Hi everyone. This is a video about how do you apply the method of initial rates given a set of data of various experiments where you have the the initial rate of the reaction and you have different concentrations. How do you analyze that and get the rate law? And so I'm going to work through the math. I'm going to work through it in a little bit more mathematical detail to sort of explain the logic of the method of initial rates. But the basic idea is we assume that the rate law should have this basic form. So here's my reaction, A and B combining to make C. So I assert that the rate law should have that basic form. It should go as the power of A, the concentration of A to some power, and the concentration of B to some power. I don't know what those powers are, and that's what we're trying to figure out. So the basic idea here is that if you have multiple experiments, you can look at, basically take the rate of one experiment and divide it by the rate of the other experiment. So I'll be writing little subscripts 1 and 2 and 3 to refer to individual individual trials. So I might say if I take the rate of the second experiment and divide it by the rate of the first experiment, well, the rate of the second experiment is equal to K times the concentration of A in that second experiment raised to the power of X times the concentration of B in that second experiment raised to the power of Y. So that's just me applying the basic form of the rate law. And then the rate for the second experiment should have a similar form. It should go as concentration of A in the first experiment raised to the power of X, and the concentration of B in the first experiment raised to the power of Y. So all I've done there is just saying I'm going to look at the ratio of these two experiments. And then I can say a few things. I can simplify this expression a little bit. First thing I can do is I can divide out the rate constants. They should have the same value. The rate constant is a constant. It doesn't depend upon the concentrations of the other reactants. So those will divide away. And I can also say, if I look at my experiment here, the concentration of B in the second experiment is equal to the concentration of B in the first experiment. So those two values are also the same, and they will divide away. So what I'm then left with is just looking at how does A change between the two experiments. So I can say rate of the second experiment over the rate of the first experiment, and I get this. That's raised to the X, and that's raised to the X. And that's what I have left to work with. So I can do a little bit more algebra here. If I have a quotient and I'm two things that I'm dividing by each other, I can factor out that exponent. Since they're both raised to the same exponent, I can factor them both out. I can say that this, or not factor them out, but I can divide them out. This should be equal to the numerator over the denominator, the whole fraction raised to the power of X. So again, now I'm looking at what's the relationship of this ratio, what's the relationship of this ratio, what factor do I need to raise this ratio to equal the rate. Okay, so that's where we're left with, that's where we're at right now, and then I can say a couple of things. Then I can look at my data and I can say, okay, the rate of the concentration of A in the second experiment is 3 times the concentration of A in the first experiment. So I can substitute that in here, and I get 3 times the concentration of A in the first experiment times concentration of A in the first experiment, all raised to the x. And then these three guys, these two guys divide away because they're equal to each other. And what I'm left with here is I look, okay, there should be some ratio here where I have 3 to the x. That 3 again notes that I ended up increasing the concentration here by a factor of 3. If I look at the rate, how did the rate change? The rate changed by 12.6 over 1.4, and again, that should be equal to 3 to the x. And if I calculate that, what I get here is this should be equal to 9. So I have 9 is equal to 3 to the x. And then I have the logic to myself, okay, the only way I can make this work is if x is equal to 2. X is equal to 2. That's not written correctly. Okay, so that's way more detail than you probably would need to work through in an actual method of initial rates reaction. But it is kind of giving you a logical throughput of how rationally you work through this. Is that okay? You see, if you change the concentration of one of the reactants to another one, and then you look at, okay, how does the rate change? If the rate increases by a certain factor and the concentration changed by a certain factor, what is the exponent I need to raise the concentrations factor by to equal the factor that the rate increased by? So let me say that again. You need to check, okay, what factor or what power do I need to, let me say that one more time. You change the concentration by a certain factor. In this case, we changed it by a factor of 3. And then you see, how does the rate change? Okay, the rate changes by a certain factor. And then you ask, okay, what exponent do I need to raise the concentrations factor by to get to the same factor that the rate increases by? And that exponent needs to be the exponent in the rate law. So in this case, we get that x is equal to 2. And then I can sort of apply the same method to figure out what's the factor for B. So you can do the exact same thing, or you can work through this whole analysis, but I'll show you where you get to. What you get to essentially is this equation, or something that looks kind of like this. So I'm going to reproduce that here, working with B now instead of A. So what I have here is the rate with respect to, well, I could do 2 and 1, but since we didn't change the concentration in 2 and 1, that won't make sense. So instead, I'll look at how the concentration changes between 2 and 3. So I'll look at ratio of rate 2 to the ratio of rate 3 to rate 2. That should be equal to, applying this here, I have concentration of B in the third experiment over the concentration of B in the second experiment raised to its exponent y. So again, I'm kind of using the same, this was like the final derived step that will be most useful for us to sort of apply methods of initial rates here. So I can say, okay, what was the ratio of the rates between 3 and 2? 3 was 4.2 molar per second, and rate 2 was 12.6. That ends up being equal to 1/3. How are these guys related? So concentration of B is 0.1, concentration of concentration of rate 2 is 0.3, so I have 0.1 divided by 0.3 raised to the y. This is equal to 1/3 raised to the y. And then I can assert that, okay, I have 1/3 equal to 1/3 to the y. The only value of y that will give me an equality here is if y is equal to 1. So that's sort of a little bit of a quicker application, and probably how you will end up applying method of initial rates more frequently. So then you can say, okay, the rate, the exponent, the order with respect to b is 1. Okay, so now that you have the general form of the rate law, how do you get the rate constant? Because that's the last thing you want to usually determine here. So at this point, we actually have all the data we need to calculate the rate constant. So I have this general form here for the rate law. So then the rate law lets me know that I'm going to divide both sides by the concentrations. So I have that the rate constant should be equal to rate over concentration of A squared times concentration of B. And then I can use some of my data, plug that in, and calculate the rate constant. So in this case, I chose, I'll just use experiment 1. I know that the rate in experiment 1 is 1.4 molar per second. And I have the concentration of A here should be 0.2 molar quantity squared. So it's the concentration of A squared divided by the concentration of B, which was 0.3 molar. If you multiply that, or rather multiply and divide through, what you get here is 116.7. And then you usually want to make sure you get your units correct for the rate constant. Different rate laws, depending on their order, the rate constant will have different units. So if you're doing it this way, you can kind of predict, you can actually figure out right here what the units should be. So I have molar per second. I'm dividing by molar squared and by molar. So those molars are going to cancel with each other. And then I have 1 over seconds and 1 over molar squared. So the units for this should be 1 over molar squared, 1 over seconds. So that's one way you can get the units, the rate constant. You could also get the units of the rate constant once you figure out the rate law. So one thing you can do is you can say, well, I know the rate needs to have units of molar per second. So for instance, you don't even need to do this entire calculation. Once you get the basic structure of the rate law, you can assert what the units need to be. I don't know the units of K yet. I know this term is going to have units of molar squared, and then this term will have units of molar. And then you can kind of work backwards and say, okay, what units does this guy need to have? What units does the K need to have to give me net units of molar per second? Well, none of these guys provide me a 1 over seconds, so I know that at the very least K will have to have units of 1 over seconds. And then I need to be left with units of molar. I actually have molar cubed here. I got molar squared times molar, that gives me molar cubed. I only want 1 molar left over, so I can divide away these molars and divide out by molar squared. Those would cancel, and I'd be left with molar times 1 over second, which gets me molar per second. And yeah, that's the same thing we got here in our explicit calculation. Okay, so that's one way to do it. I thought I would do one more example here. Somebody asked, what happens if
things don't divide neatly. What happens if you have cases where you're not multiplying by 3 every time or by even numbers? That's when you really, really need to use this mathematical approach. And that's one reason why in this video I explicitly worked through this. In the worksheet, I just kind of want people to notice, okay, if I double something, the rate quadruples. If I, or that means it's second order. So I worked with with mostly integer factors there, but let's say I had a slightly more complicated set of data. So I'm only going to look at one particular order here. So let's say this was my data that I was working with 1.25 molar of A, and I didn't change its concentration between the first and the second step, but I instead changed the concentration of B from 1.25, not neatly into 2.5, but to say 3.02. So I'm just going to multiply it by some random, not random number, but yeah, but some random number. And then the rate for this reaction might be 8.7, and the rate for this reaction might be 50.8. So I can still use the same approach I had before. All the same previous logic we worked through that led us to this expression that the ratio of the rates needs to be equal to the ratio of the concentrations raised to the exponent of that compound in the rate law. So let me make sure everything matches up here. I'm going to have 2 to 1, so I'll change my labels here. These are just labels just to make sure everything is neat and organized. This is what we have to work with. So we can still apply this using these non-whole number factors. So the rate increases, how do I want to say this? So let's look at this. The rate increases by this factor. So rate 2 was 50.8 over 8.7. That ends up being an increase of a factor of 5.84. So yeah, definitely not a whole number increase. So that's just the ratio of the rates. This factor here ends up being a factor 3.02 divided by 1.25. Again, it needs to be equal to that raised to the yth power. that has a, you got to be careful pronouncing that. Anyway, this factor here is going to be equal to 2.146. Oh, sorry, 2.416 raised to the y power, 5.84. So yeah, what do you do with this? That's trickier. That one it is not obvious what the value of y should be. In that case, I recommend using logarithms. And what logarithms are is a mathematical tool to take things from an exponent and get them out of exponents. So what I will do is I will take the natural log of this entire equation. I'll take the log of this, and I'll take the natural log of this whole expression. So you could do a log base 10, you could do natural log, all the same rules for logs will apply here. And it's a general rule of logs that if I have natural log of a to the x, that's the same thing as x times natural log of a. So I can take an exponent inside of a natural log and bring it out of the exponent. So that I can do that here. And what I'll be left with is natural log of 5.84 is equal to y times natural log of 2.416. And I can calculate natural logs on a calculator. I can calculate this natural log on a calculator. So now I can solve for y
and calculate this. So I'll divide both sides by 2.416, natural log of 2.416, and I have y is equal to natural log of 5.84, natural log of 2.416, and if you plug that into a calculator, you get something that's pretty darn close to 2. Small enough difference that it's probably just due to rounding error somewhere. So, short answer being that if you have data where it's not even numbers, or if you're getting weird, bizarre numbers, that's when you kind of need to explicitly start from this mathematical approach, or this mathematical expression, that we expect that, okay, if I have a ratio of rates, the ratio of their concentrations in those two experiments, this should be equal to the ratio of their, the ratio of rates should be equal to the ratio of the concentrations raised to their exponent in the rate law. So let me give you an example. I'll apply this idea for one of the example problems that was on the worksheet. So the example problem here was this. So I'll do trials 2 and 3 is specifically the ones I wanted to look at here. 2 and 3, my concentrations were 0.100 and 0.050, 0.100 and 0.10. So this is 0.029 and 0.041. This was the rate. This was the concentration of chlorine, and this was the concentration of chloromethane. So I can apply the same method here. So you might be able to apply this and see that, okay, this guy increases by a factor of 1.41 some odd. That is not obvious that that goes as the square root, or the square root. So let me show you how you can get to that a little bit more neatly by applying this. So we'll say that B here is Cl2. So what I have here is 0.041 over 0.029. That's going to go as concentration here was 0.1 over 0.050 raised to the y. So this ends up being equal to, actually I can calculate that. 0.041 divided by 0.02 is 1.414. I'll round it off there. This is going to be 2 to the y. So I can take natural log of this, natural log of this. I could bring down the y, and I have y times natural log of 2 is equal to this guy. So I'll just keep that there, natural log of 1.414. And then I can solve for y. I have y is natural log of 1.414 over natural log of 2. And if you calculate that, you get 0.414 divided by natural log of 2. You get 0.4998. And that implies that y is equal to 1/2. So this is an example where the rate law doesn't go as an integer factor, it goes as a fractional factor. And those definitely can pop up from time to time. So I hope this this was helpful. Please let me know if you have further questions or if you'd like a few more videos like this. I'd be happy to try to create them for people. All right, I hope everyone has a good weekend.